I think Milton gave the thumbs up.
That was a thumbs up? Okay, good.
Yes.
Okay, so let's start. It's a great pleasure to have Nikos with us, Nikos Zygouras from the University of Warwick, and he will talk about the critical 2D stochastic heat flow and SPDEs at criticality.
Okay, thanks, Ines. So it's yes, very nice to connect with you online. I have been to Buenos Aires, but actually I think shamefully I have to say that probably I'm the only probabilist who hasn't been to Brazil yet. I need to come at some point. And yes, but in any case, it's a great pleasure to be connected with you. So can you hear me well? So at some point, if you cannot hear me well, Milton will do thumbs down. Okay. Right. So I'm going to talk about some series of works mostly done with these two good friends of mine, Ron Frank and Francesco. And so it's going to be around the stochastic heat equation. And eventually it's going to go to the object we constructed, the stochastic heat flow, the critical two-dimensional stochastic heat flow. And I also want to see this as a kind of door towards some efforts building a theory towards PDs at critical dimension or critical SPDs. Okay, so let's start with the stochastic heat equation. So, of course, everybody knows that the stochastic heat equation is given by this top line. It has the heat part and the white noise psi multiplying the solution. And here I want to motivate the criticality of the dimension. And so dimension 2 turns out to be critical. Let's see why. Always the problems with stochastic PDs is when you multiply distributions. So noise is a singular object, and then giving a meaning to a multiplication with a singular object is a touchy business. In dimension 1 for the stochastic heat equation, this is easy to be done. For other nonlinear SPDs, now we have a full-fledged theory below critical dimensions. But let's see what happens at the critical dimension. Let's see what is a critical dimension, first of all. Right, so one way to study the regularities, if you want, of the solution of an SPD is to renormalize it. So scale space and time in this parabolic way. So T over epsilon squared, X over epsilon, and see what equation the U epsilon satisfies. So if we do this and we use the scaling of the space-time white noise, U epsilon satisfies a stochastic heat equation similar to the above, but with an epsilon to the d minus 2 half being spit outside the white noise. So now this white noise has a different symbol than the one above, because the two objects will not be the same, but it will be the same in distribution. And now, if we want to study, let's say, if we study statistical mechanics, then we want to send epsilon to 0 and see what is the large space-time statistics of the solution. If we study SPDs and we identify about regularity, we send epsilon to infinity. So then this time becomes small and the space becomes small. No matter what, so we see that when d is different than 2, this factor epsilon, when epsilon goes to 0, when epsilon goes to infinity, will lead to either a negligible contribution of the noise term. So maybe if you are, if this factor here goes to 0, then formally you can say that this becomes negligible, and then the stochastic heat equation becomes a perturbation of the heat equation. Or if this prefactor goes to infinity, then the noise part will have a dominant effect. So in dimension d equal 2, though, formally this vanishes. So you have epsilon to the 0. So the prefactor in the singular term, you don't see it in the renormalization. And to decide whether the noise will have an effect to the solution or not, you need to start looking much more carefully into your problem. Right. So this scaling argument justifies what is in SPDEs called criticality. But actually, Francesco, Renfeng, and I came to this because we were studying disordered systems, pinning models, and so on, where actually the terminology used for the same thing was marginality. So in disordered systems, you talk about marginal relevance if the noise has a dominant effect, or marginal irrelevance if the noise has a negligible effect. And when you are at a critical dimension, you talk about marginality. And then the noise can have an effect which is marginally relevant or marginally irrelevant. And to decide what it is, you have to look much more carefully. Okay, so this is about the critical dimension. But how do we proceed making sense of the stochastic heat equation? Right, so the standard procedure is to smooth out the singular object. So we mollify the noise by convolving with a smooth test function. And then in general in SPDEs, after we do this mollification, we want to take the mollification away. So we want to send epsilon to 0 and see if we can get some meaningful limit. For the stochastic heat equation in dimension 1, we can do this procedure and we can get a bona fide limit. And in dimension 1, we don't need to do anything with the prefactor of the noise, with the temperature in front of the noise. However, at a critical dimension, we need to do something more drastic. We need to do some extra renormalization, which incarnates here by replacing tuning the temperature in front of the noise in this very, very particular way. So beta hat, and this beta hat is going to play a role because I'm going to be seeing phase transitions here in the beta hat, times square root 2 pi log of 1 over epsilon. So we do this renormalization, and we ask if there is a sensible limit of the solution u epsilon. Now one can immediately object and say, okay, now you send beta epsilon to 0, so you just kill everything. But that's not the case, because beta epsilon goes to 0, but the xi epsilon will go to infinity. So there is the issue of what is 0 times infinity. And at a critical dimension, this is subtle. Okay. Right. So let me now say a few of the results that we had with Francesco and Renfeng. So the first result we had a few years ago was that if you do this procedure that I described in the previous slide, u epsilon for any fixed space-time point, if you look at the solution point-wise, then the statistics of the solution will converge to either a log normal distribution, so the exponential of a normal, x is a standard normal variable, and then sigma beta has this particular form, log of 1 divided by 1 minus beta hat squared. And this will happen if beta hat is strictly less than 1. So I recall that beta hat is the tuning of the temperature. On the other hand, if you hit this critical temperature beta hat, then at any point of space and time, the solution will go to 0. This is far from saying that actually at beta hat at critical temperature, the solution is 0. So we will see that something interesting happens. That we have the development of intermittency and the emergence of strong correlations there. But I'll come to this point later. So this result, first of all, identifies the phase transition, beta hat. The second result we had in the same work with Francesco and Ronfeng was to study what happens at the solution, not viewed point-wise, but viewed as a field. So what we do here is we take the solution at a point t at x, and we average, we test it against the test function phi of x. Now, if we rescale by log of 1 over epsilon over square root 2 pi, then the limit will converge to the average of another field, and this field will be given by the solution of the additive stochastic heat equation. The additive stochastic heat equation has a number of equivalent names, is a Gaussian free field. And in general, this convergence, which is a central limit theory for fields, is also known as the Edwards-Wilkinson universality. Now, two things I want to remark. The first one is the scaling of log of square root log 1 over epsilon in front of the average. This basically tells you that if you look at different points of the solution, these points decorrelate. And decorrelate at speed 1 over square root log epsilon. And then if we blow up this decorrelation, then we see the central limit theorem. As we see, when we hit beta hat equal 1, we will not need to do any rescaling. So this will give a rise to the strong correlations. The emergence of strong correlations beta hat equal 1 also can be seen by the prefactor here. So in the additive stochastic heat equation, the fluctuations of the driving noise, which actually is different than the original noise of the stochastic heat equation, will start blowing up. Okay. Right, so this I put it in green because we will see the emergence of something similar in a few other examples that have been worked out. And one of the questions is actually to be able to determine really what is that gives rise to this prefactor, to this particular constants. Okay, so let me discuss a few other examples of SPDs at criticality, at critical dimension. So the natural one that you discuss after you discuss stochastic heat equation is the KPZ equation. So the KPZ equation is this one. You mollify the noise, you tune it in the same way that you tuned the stochastic heat equation. And then here you also need to subtract a constant, which is basically the L2 norm of the noise. One thing that we proved with Francesco and Ronfeng is that the solution of the KPZ equation with the same scaling has the same limit like the stochastic heat equation, like the previous slide. Will converge to exactly this solution of the additive heat equation with the same tuning of the noise. One difference is the centering here. So actually this also indicates that going from the stochastic heat equation in this particular case is not just linearizing, okay, is linearizing the logarithm of the stochastic heat equation. We know that the stochastic heat equation and KPZ are related by the Kohlhoff transformation, which is if you set H equals log U, then you can go from the stochastic heat equation to the KPZ equation. But this is not going from the fluctuations of the critical stochastic heat equation to the critical KPZ is not a simple Taylor expansion. Log of 1 plus x is almost equal to x. Gu also proved the same result, but not in the whole subcritical temperature regime, a few weeks after us. And then a bit earlier, Chatterjee and Dunlap had also looked at the KPZ equation and they proved tightness of the field. And this result actually is that the result that inspired us to motivate us to prove the Edwards-Wilkinson for the KPZ equation. Next SPD is an anisotropic SPD, an anisotropic KPZ. So the difference here is the plus became minus, and I see a typo here. So here I have the gradient with respect to x, and here should be the gradient with respect to y. So we have Edwards-Wilkinson limit for the anisotropic KPZ, not just because the typo here, not just because this difference is zero. Okay, so the one should be gradient x minus gradient y. So this has been studied quite extensively, starting with works by Dirk, Erhard, and Canizaro and Schoenbauer. I have the first work down here, and then developed further also Toninelli has joined, and more recently Gubinelli has joined. And they proved that if you scale the nonlinearity in the similar logarithmic way that I scaled the stochastic heat equation or the KPZ, the isotropic KPZ equation, then the solution to the anisotropic will have Edwards-Wilkinson fluctuations, and then it will converge to this additive stochastic heat equation, but with a different strength of the noise and a different also diffusivity. So that's a difference, one of the two main differences with the isotropic KPZ equation. The isotropic KPZ equation, we only see a prefactor emerging in front of the noise, but not in the Laplacian. Another difference between isotropic and anisotropic KPZ is that we don't see a phase transition in the anisotropic KPZ. So you see the strength of the noise doesn't blow up at any lambda. Right, okay. Maybe one more example, and essentially this will almost exhaust the known examples for nonlinear for SPDs at critical dimension. Is some nice works of Dunlap and Gu, and actually Dunlap has been developing this further with in works with Cole Graham. They look at a semi-linear stochastic heat equation. So instead of u times the noise, you have sigma of u times the noise. And they scale it again in the same logarithmic way. And the first result that they prove is that if the Lipschitz constant is less than square root 2 pi, actually you can see this square root 2 pi to be the same square root 2 pi that I had in the stochastic heat equation. What I proved is that if you look at the solution to the semi-linear stochastic heat equation at this exponential times, exponentially scale times, so you have epsilon to the 2 minus q, your effective time now will become the q. That's a feature actually that happens at criticality, and that's something we had already observed in the works with Francesco and Ron-Feng. Then the solution at this time scale will converge pointwise, not to a log normal distribution, but some distribution which can be realized as a solution of a forwards-backwards stochastic differential equation. Okay. So that's actually a very nice feature. So in the case that sigma is linear, you can solve explicitly this forwards-backwards SDE, and then you get a log normal distribution. Another case where you can solve this is when sigma is square root of u. I forget what they get in this case. But there is something very interesting in this forward-backwards SD. Right, and Ran Tao, a student of Yugu, was able to extend the pointwise result to a result in terms of fluctuations. So if you look at the field of u epsilon for various space-time points, then this will have Edwards-Wilkinson fluctuations, will converge to the solution of this additive stochastic heat equation. And now here again, there is a different constant in front of the noise. I think really one of the features that is quite intriguing to me is to be able to actually understand how these constants, different constants emerge. We had a different constant for the stochastic heat equation, a different constant for with the same constant for the isotropic KPZ, but a different constant for the anisotropic KPZ, and a different constant for this semi-linear stochastic heat equation. And hopefully at the end of my talk, I will show another example where somehow for an Allen-Kahn equation, where there appears to be an ordinary differential equation governing this constant. Okay. Hopefully we'll come to this point. Right. Okay. So the results I discussed so far was the few results of critical SPDs that we know, but all of them below some critical temperature. So below the beta hat equal 1 for the stochastic heat equation, below this Lipschitz constant having a value square root 2 pi for the semi-linear heat equation. And the result we obtained with Francesco and Feng, the most recent, was actually to prompt what happens at the critical temperature. So here should be a 2 pi. Pi should be equal to 2 pi. So when we hit the critical temperature, we saw two features. If we look at point-wise, the solution just appeared to be 0. Or if we looked at the field, the driving noise was becoming crazy, right? The strength of the driving white noise in the additive stochastic heat equation was becoming square root 1 divided by 1 minus beta hat squared. What we proved with Francesco and Feng is that if you look at the stochastic heat equation at the critical dimension 2 and at this critical temperature scaling, and you average, then you will converge as a field to the average over what we call the critical 2D stochastic heat flow. And we know some things about this object, but there are many more things that we should understand. So what we know that it's a low correlated field. It has covariance structure very similar to the Gaussian free field, to the additive stochastic heat equation. But this field is not Gaussian. And moreover, another thing that we proved is that it is not the exponential of a Gaussian, meaning that it cannot be a Gaussian multiplicative chaos. This might give some evidence that when you look at a critical two-dimensional KPZ equation, so this means critical dimension 2 for the KPZ, and at this critical scaling of the temperature, the solution should be non-Gaussian, but this is far from proved. Okay, so this is actually one of the challenges. Can we transfer these results to the KPZ equation itself? Right, so the third bullet says that what we get is not 0, as we would imagine. One of the results I showed earlier is that if you put your finger at any point at a critical temperature, the solution will converge to 0. But actually, if you look at it globally, it converges to a measure, a random measure. And actually, this measure is singular with respect to Lebesgue, which is why at any fixed point, the solution will go to 0. And we also have some hints of self-similarity, so that this object has some self-similarity, which I'll try to convey later on. So we know a few things, but there are many more things that we don't know. In particular, can we say how this object looks like? And yeah, here comes the picture. You may be wondering why I had this at the beginning, not only because it looked hot, but okay, so here is a simulation I did for 66,400 steps of the direct polymer model. Okay, I'm going to come to the direct polymer model soon with flat initial conditions, and then okay, it may look like Brace Canyon. Okay, or with Dirac initial conditions, it looks like this place in Greece. This is in the middle part of Greece, where you have these rocks kind of popping out of the valley. Or it can look like Dubai. Usually when I am in live, I hear people laughing, but I don't hear this now. Okay, I think maybe hopefully you laugh or it's not a joke. Right, okay, but what we see, okay, is that we see some patches. So we see the singularity, but we also see some patches. So then you can ask some questions, okay, what is the Hausdorff dimension of the support of this measure? I'll come to some questions later on. Okay, we would also like eventually to take the logarithm of this and build the critical KPZ equation, which should look like a surface growth, like the Alps. But these are all simulations, and we would like actually to develop the methodology to quantify these pictures. Okay, I don't know if there are any questions before I go to maybe some of the methods. So do we have any questions about what I'm talking about? Okay, so I think I have about half an hour, probably, right?
So, Nicholas.
Yes.
So at the beginning, you show us that there was a dichotomy on beta. This one, yeah, exactly. So so you go to this e to the something, no?
Mm.
So that's something does it have a spatial structure, or is it just
This is okay, right? Okay, so that's a good point. So this is if I fix any space and any space point, then the distribution of this object will be log normal. Now you can say, okay, if I have a different, if I evaluate this log normal at a different point, what do I get? What you will get is that independent normals. So at one x and at another x, you will be seeing exponential of independent normals. And that's why if you want to study as a field, that's why, if you average, basically you average independent random variables. So you have the central limit theorem. And that's why you need to blow this up. One thing that is more interesting is that if you go essentially here, when you do U epsilon, essentially you go to diffusive space-time scaling. So you have x to be at scale 1 over epsilon and t to be at scale, 1 over epsilon squared. So the different points live at scales 1 over epsilon, the different space points at scale of 1 over epsilon. But you can say, okay, what if I look at scale not 1 over epsilon, but 1 over epsilon to some power xi, with this xi less than 1. Then what you see is that you see similar log normal limit, but these normals here will be correlated. And the correlation will have this logarithm 1 minus the xi, the exponent in the epsilon, beta hat squared, divided by 1 minus beta hat squared. So just to answer your questions, if you go at the diffusive spatial scaling, then you see independence at beta hat less than 1. If you go slightly subdiffusive, you start seeing correlations. But when you hit a critical temperature beta hat, you already start seeing strong correlations at diffusive scaling, spatial scaling. And that's why here you don't blow up anything. So it's not that anymore you average independent random variables. The random variables that you average here will be correlated. Yes, I think that was a good point. Yes. Okay, so the next is I would like to discuss some of the methods of how we obtain results, both at subcritical temperature and at a critical temperature. Okay, so I'm going to switch from continuous to discrete because this is a bit more convenient for us, but you can essentially do everything in the continuous setting. What we do in the discrete, we can do it at the continuous setting. Right. So for the stochastic heat equation, we have an explicit expression for the solution, which is a Feynman-Katz formula. So psi here, you should see it as the initial condition of the stochastic heat equation. So you average a Brownian motion Bt over the initial condition and discounted by this Feynman-Katz exponential, which is e to the integral of the white noise average along the path trajectory minus half the quadratic variation of this stochastic integral. And passing to the discrete is passing to the direct polymer model. Zn will be the partition function of the direct polymer model. So here, instead of averaging with respect to a Brownian motion, you average with respect to a simple two-dimensional random walk. And instead of having a space-time white noise, you have the discrete analog of it, which is a family of independent random variables, omega, at every point of the space-time lattice. And the standard conditions we have for this partition function is that for the disorder is that it has mean 0, variance 1, and exponential moments. Right. So we also consider the average partition function, but so you average the starting and the end point of the polymer of the polymer. Is this setting clear? Okay. Right. So once we have this exponential, we expand it, and we go to the chaos expansion. If you are not familiar with expanding the exponential and doing the chaos expansion, you can think in terms of PDEs. You can use Duhamel formula for the stochastic heat equation. You can start iterating, doing the Picard iteration. And if you do the Picard iteration, you'll get a series of this form here. So what do we have here? So this chaos expansion goes as follows. You pick k points in space and time, where at these points, I'm going to sample the noise that I see. So I have psi, the noise, which has some strength beta n in the discrete or beta epsilon in the continuous. And then you ask the random walk to jump from one side to the other. So Qnx is the probability to go from 0 to n, from 0 to x at time n, and then go from point n1, x1 to n2, x2, and so on and so on. Okay. Is this clear? Okay, maybe. Can I see some thumbs up or some thumbs down? Some impulse? Okay, good, okay. Right. Okay, so one thing that happens when the temperature is beta hat strictly less than 1 is that the picture here is misleading. So the points that the main contribution to the fluctuation of the partition function will not come from spread out points. Instead, it will come from points which have time gap n to the alpha for any alpha less than 1. So actually, these gaps that you see here are very much concentrated close to the origin, a little off n. And so we obtain this by some variance computation, some fairly simple variance computation. And so the structure that emerges is the following. So you will have a first jump where you sample noise, and then you will go sampling noise very close. So the gaps that you see here will be much smaller than the first gap that you see. And then you will make a bigger gap. So it will be, let's say here will be n to the alpha 1. And then here will be n to the alpha 2 with alpha 2 bigger than alpha 1. So n to the alpha 2 will be much bigger than n to the alpha 1. So the second, you wait until you see the second big gap. And then after that, you see small gaps for the next sampling points. So you have this kind of hierarchical structure, and one thing that happens, which is, okay, it was not obvious to us at the beginning, and then actually we didn't expect it, we expect something different, is that this, so this will be a multilinear polynomial. If you just look at the first bubble, it will be a multilinear polynomial of the noise. And actually what happens is that this multilinear polynomial will converge to a normal random variable. And the other bubble, the other multilinear polynomial, will converge to another random variable. And these two will be uncorrelated because they sample different space-time points. And the other thing that happens is because this gap, here is a transition probability from 0 to this point, and here is a transition probability from this point to that point. But actually, I can essentially, the probability to go from here to here will be the same as the probability to go from 0 to here, because the scales are too big. So you cannot see whether this point is at 0 or not. And then this introduces factorization. And this factorization is actually what, together with the with the normality that I see here of the thetas, is what leads to something that eventually you recognize as the expansion of the exponential of a normal variable. Okay, this I understand very fuzzy, but maybe let's try to keep this picture that when you are at beta hat less than 1, you have this separation of scales, and you have some limit theorem happening, central limit theorem happening at the constituent scales.
So,
and all it leads to an expansion of an exponential, yes.
So in the bubbles, how many points do you have usually?
Yeah, you can have yeah. So here, of course, we fix here. I have fixed the points, but eventually you're going to be summing up. There is a summation. There is a number of summations that is done. Yes. Yeah. So here is the theorem is for any fixed number of points that you have. Yes. You have this log normality. Yeah. But then you did need to perform a number of resummations. Yeah. You have to do this decomposition. Yes. So once you have K fixed, then you decompose it to how many points you have, fixed number of points in the bubbles. Each one will converge to normal, and then you need to do a swap of the summations. Yes. Yeah, it's not obvious, but maybe let's just keep the picture that in the point that in subcritical temperature there is this exponential time scale, which leads to a separation of scales. That's the important point. And that's not what happens at the critical temperature. So at the critical temperature, the main contribution will not come from sampling of noise at time scales little often, will spread out all over. And then the approach here is to organize and move ahead is to do a coarse graining. So on the top picture is my chaos expansion, which samples points everywhere from 0 to time n. And then I partition the space time into these blocks of time duration epsilon n and spatial width square root of epsilon n. And then I ask, okay, which of these blocks are visited by my chaos expansion? So this is, we have been working a lot before getting into this business, into pinning models, where Hubert with Fabio Toninelli and Giampattista, actually they advocated and pushed this coarse graining. So having learned from Hubert and his buddies, then we were able to transfer this to this setting. And now one point is that, if I start, let's see if I can do it. Yeah, if I start zooming out, I guess the two pictures for you are the same, right? You just see something and some dots. So the idea was, yes, to perform this kind of scaling out. How? Well, here there is some complicated disorder happening at each block, and then this is difficult to track. So what I want to say is that, okay, I want to put forward the Lindeberg principle. So what you have below is a multilinear polynomial of the coarse grain disorder, where at these coarse grain blocks I have some sampling happening, some basically partition function, which is complicated. But then, okay, I can take the whole block out and remove and replace it by some independent Gaussian. If I can do this in the large n limit, and large n limit is basically going to this picture, okay, then yeah, basically this replacement will allow you to do the large n limit. I don't know, is this clear what I'm trying to do here, what we're trying to do? So we're trying to put forward the Lindeberg principle. So below you have a multilinear polynomial of this coarse-grained disorder. And then I want to go and replace this random variable, the coarse-grained random variable, by something else, something independent, something that has nothing to do with my problem. This I can do in the large n limit, and then I take epsilon to 0. And this is what allows to say, okay, eventually we will have a unique limit as n goes to infinity in distribution. Okay, so in order to put forward the Lindeberg principle, so Lindeberg principle says that, okay, if you have some complicated function of the IID random variables, you can replace the random variables that you start with your favorite Gaussians, as long as the two families of random variables have the same first, second moment, and then you have bounded higher moments of the disorder, so that you can do the replacement. You can do the Taylor expansion. So my coarse-grained variable that I want to replace with some independent Gaussian in the large n limit is this, the chaos expansion of a partition function inside the coarse-grained block. Okay, so here is basically you average the starting point. That's why we have 1 over n squared. And then you start sampling points here, and the number of points that you sample is indefinite. It's not like in the previous time I was saying you fix. Here it would be indefinite. So we would like, in order to apply the Lindeberg principle, to say that, okay, this variance of this coarse-grained random variable stabilizes. And as n goes to infinity, actually turns out to be 1 over log 1 over epsilon, which is the scaling I was doing of the noise since the beginning. But most crucially, the constant that I see here is again the critical constant. So if you want, this is a type of renormalization. So you have your coarse-grained renormalization, and you take this coarse-grained complicated object, you replace it. But when you replace it, actually the statistics of this coarse-grained object are the same as the microscopic ones. So somehow in this renormalization approach, you are in a kind of a fixed point. If the constant I was getting here was less than 1, then maybe I would have a contraction to something trivial. Or if the constant I was getting here was bigger than 1, then maybe I will will not have a limit. So this type of estimates, obtaining these estimates, was very crucial. And for this, we linked to we developed some renewal structures. So we're able to do precise variance computations. And okay, maybe I will not go too much into detail, but link to something called the Dickmann subordinator. Okay, maybe just keep in mind that we have a way to obtain very precise second moment estimates. Okay. The next thing that we want in order to apply the Lindeberg principle is to say that, okay, we have first matching first and second moment. And then we also want to say that we have bounded higher moments. Now, if you compute the, let's say, the fourth moment of the partition function of a direct polymer model, a simple computation leads to saying that this is actually equal to the exponential moments of the total collision times of 4 independent random walks. So you can imagine that you have exponential of the summation of the collision time, pairwise collision times of 4 independent random walks. And the question is whether these moments actually, the collisions, the exponential moments of the collision are finite. And this is, this is kind of a subtle issue that actually was also, has been of interest in mathematical physics in people who studied delta Bose gas. Right, so let me see how much time I have.
I would say 5 minutes.
Okay, okay. Maybe then I will not go into too much detail, but okay, so how do we handle this? So we want to break the evolution of the walks and the collisions into strips, and then having a Markovian evolution. This will be a convolution, and then if you want to go to simplify, you go to the Laplace transform or to the resolvent. So here you have this, you sum exponential negative lambda n of the total collision time of 4 walks starting at these points. Okay, maybe I will not go into too much. I think this will need a blackboard as well, or I can come later on back to this. Maybe I want to mention here a few things that here we had to develop some Hadley-Littlewood-Sobolev inequalities, so of this form, to develop further inequalities done by the Lantonio Figari Theta, and then actually this was we were inspired to do this by work of Gu, Castell, and Tsai, who were actually able first to do higher moments of the stochastic heat equation in the continuum. In the first paper with Ronfeng and Francesco, we were able to do the third moment, and then Gu, Castell, and Tsai, with a different approach, were able to obtain all moments of the stochastic heat equation, and then we refined this in order to be able to work in the coarse graining setting. Yes, okay. Okay, maybe just closing. Yes, I want to show the pictures of these two handsome men. So the one is Simon Gabriel, who was a student of mine, and now he's a postdoc at Münster. And then Tommaso Rosati. Here we also, that was a kind of an example, an attempt that we made to look at nonlinear SPD, but without doing any linearization. So we looked at this Allen-Kahn equation with white noise initial condition, scaled again in this logarithmic way. This turns out to be a critical SPD. And I just put this picture also to compare it with the chaos expansion diagrams that I had before. So when I had the stochastic heat equation, the pictures I had was this kind of linear sampling. If you go to the nonlinear setting, then people who have done regularity structures have seen this emergence of trees. So here we will have the emergence of trees, so that will replace the chaos expansion that I had in the linear setting. And yeah, when you look at when you are at the critical temperature, these logarithms here leads to some kind of collapses, collapse of scales. So, okay, I will not go into much detail. Eventually, the result that we have here is that U epsilon will converge to, again, an Edwards-Wilkinson limit. but with a different constant, which I think I don't have it in my slides here. Okay, maybe just to close up, some questions and directions. So, right, I spent most of the time talking about this object, the critical 2D stochastic heat flow, which we know it exists. We have constructed it. We know some of the things some of its features, that is not Gaussian, that is low correlated, that is not an exponential of Gaussian. But can we have an axiomatic characterization of this? So we would like actually to see this as a new universal object. And having an axiomatic characterization, of course, will be very useful to say, okay, if you have any object that satisfies 1, 2, 3, 4, and 5, this has to be the critical 2D stochastic heat flow. And if you have any other object that is a perturbation that has 1, 2, 3, 5 in a perturbed way, then this has to converge to the critical 2D stochastic heat flow. So I would like something similar to, let's say, the axiomatic characterization of the Gaussian free field. The Gaussian free field is what it is this low correlated object which satisfies Markov domain Markov property and some conformal. So can we develop something similar? And then, okay, number 3 says that, okay, we know that is not a GMC, but what is the relation to GMC and other related theories like Liouville quantum gravity? It's not a GMC, but is it singular with respect to any GMC, or is it absolutely continuous with respect to some GMC? Can we say something about the fine properties of the measure, like the support of the measure? What is the fractal dimension, or what is the structure of the maxima and the thick points? So here you have a low correlated object, and low correlated objects have been studied extensively, in particular in relation to the structure of the maxima and the thick points. Can we say something similar about this? There are some interesting questions about the asymptotics of the moments. So just to relate to the one-dimensional setting, the exponent 1/3 that Cardar-Parisier-Jung predicted emerged also from the work of Cardar on study of the moments, the asymptotic of the moments of the stochastic heat equation and the relation to the delta Bose gas. So here, the moments will grow. The conjecture is that they will grow like e to the p, if you look at the pth moment. Of course, moments that grow so fast will not determine the distribution, so you need to do other things to determine the distribution. But assume that we can find the precise growth of the moments. Can we transfer this to something about the distribution of the object, something about the tail, or I don't know. The normalization of one point. So we saw that the dichotomy that also Milton asked is that if I'm at beta hat equal 1 and I look at any fixed space-time point, the solution will go to 0. But how fast does it go to 0? This is analogous to what happens at the critical GMC. If you look at the GMC at the critical gamma, then it will go to 0. But then if you multiply by square root 1 over epsilon, then you see something non-trivial. Can we do something here? Here we conjecture that we need to multiply by square root log 1 over epsilon. But okay, this is still, yeah. And finally, okay, push towards some, theory of critical SPDEs. Can we start collecting more examples and see the fundamental features that will allow us to transfer to a fully nonlinear setting? And I think, yeah, I would like to close here. Maybe, yeah, okay, maybe with this picture. So maybe a kind of a goal is that, okay, if I give you these pictures here, can you say which ones come from GMC and which comes from the critical stochastic heat flow? Or can you say which one is a two-dimensional critical KPZ and which one is a Gaussian free field? So it would be very nice to develop some methodology that, we can just test the pixel and say, okay, this pixel belongs to that class, that pixel belongs to the other class. Okay, and I will stop here and thank you very much for your attention.
Thank you, Nikos, very much.
Thank you.
And now, are there any further questions?
Yes, Ben.
Yes, Nikos, I was wondering if the critical to the stochastic heat flow, it's kind of it's the equivalent of the scaling limit of the partition function of the directed polymer, or like the equivalent of the scaling limit of the transition probabilities between two time marginals of the directed polymer. But can you push the methods you have to obtain the scaling limit of the directed polymer measure when you scale the temperature as you did, like beta hat?
You mean the path measure, the polymer path measure?
Yes.
Yeah. Okay.
Let's say that your initial distribution is not Dirac, because if that's the case, then you might have some trouble.
So okay, one
start
thing
with-
that so we call this stochastic heat flow because we expect that the partition function has this Markovianity. This is something we didn't prove, but Jeremy Clark has actually established that it has a Chapman-Kolmogorov equation, let's say the Markovian property. Then it's a different business to go to the polymer measure. Yes, Clark and also Yuting Chen, they looked at the annealed version. So if you don't look at the polymer measure, but you look at the annealed polymer measure, and this is actually you tweak the Brownian motion, you tilt it by so let me say it in a different way. So they look right. So here is a fourth moment, which you can express it as collisions of four independent random walks. But what Yuting Chen and Jeremy Clark have been looking is what happens if you have the, let's say, random walk measure of four independent random walks, and then you tilt it by the collision, the total collision time. And so there is so this is not the question you ask. So the question you ask, no, we have no idea how to do it. So this is an easier question, but still quite challenging to describe, how, you have a system of interacting diffusions. So you have these Brownian motions interacting through the collision local time. Can you describe this picture as an SDE? And this is some work that Yuting Chen has done, and also Jeremy Clark has done. And when you are at a critical temperature, you get quite a bit of singularity, right? Because, okay, two-dimensional Brownian motions will never meet. Now, if you tilt it by the collision local time, if you are at beta hat less than 1, they will still not meet essentially. But if you are at a critical temperature beta hat equal 1, you'll start seeing some attraction. So they will stay together and they will become more compact. Okay, so this is a baby picture of the question you are asking, Hubert. But still, even this baby picture has quite lots of interest of how these diffusions, to understand the interaction of these diffusions. Yes. For the question you want, yes, yeah, no idea. Yeah.
So Nikos, from what you were saying, so the message is that in this scaling limits, this scaling limits is the difficult question, no? Because you have to look at all the scales, no, to get the limits, no?
So the scaling limit of what? Of the stochastic heat flow?
Yeah, I mean, if you want to prove
Yeah,
something like universality, something like that.
yeah. So you have to look at all scales of order n. In the subcritical scale, in the subcritical temperature, you have to look at scales n to the alpha, which actually was leading to a separation of scales. And now, if you hit a critical temperature, the fact that you're kind of spread over brings out more dependence, while in the subcritical temperature, you still have independence. You can also see the dependence from this diagram here. So if you have 4 Brownian motions, they will want to sample a similar kind of places where the noise is favorable. And how this will move is a kind of complicated. If you were at a subcritical temperature, essentially these paths will not meet, will sample different things. Yes. So the difficulty comes that you have dominant noise everywhere from 0 to n, and sort of in a kind of equivariate way. So I don't know if I saw some pictures. Yes, so yeah, okay. Somehow there is some localization happening, but yeah, in a kind of way that we need to understand a bit better. Yes. Yeah, so at a critical temperature, you start seeing the emergence of localization, if you want, maybe. This reminds you of somewhere, where you have been there.
Yeah, I see I've been there. This is where monks lived and
Yeah, you have been there. Okay. Yes. I could also put a picture from Vietnam where they have these rocks, or probably also somewhere in Brazil. But okay, this is it reminds me of my home place, like King Kong. You know.
You're from there?
No, but I'm from Greece. Yes. No, I'm not from there. I have been there. It's quite interesting place. Yes. And another kind of question is that, yes, how these patches kind of move. So if you, yeah, I haven't shared with you a simulation. So how would these patches, if you run the simulation, we'll see kind of moving around, right? So how do these move? And are they kind of dense like here, or spread it out, or yeah, I think also to understand this from a dynamical point of view, how these localization points move around. I think it's interesting. It's very much related to the question that Milton was pointing.
Yeah, I was wondering. Okay, maybe it's already over time, but you were talking about the fractal dimension of the support. So for instance, if you fix the initial condition U, and okay, it's a nice function. Yeah, you wouldn't be able to say. I thought you had managed to figure okay, not something precise, but at least that the support of the dimension was
Yeah, so
was 2. I mean that the like
2
the
minus 2 minus. It should be 2 minus. Yes, there is some work in progress in this. So it's 2 minus. So and so it has let's say some logarithmic corrections. And actually you can, yeah, so you see we are at the point where we start seeing the emergence of localization also, right? So we're kind of, the support is kind of two, and you see it here is kind of thick if you look at it, but it will have lots of, you know, it will be like a dense porcupine, right? So yeah, you see these patches, so, but just starts collapsing. So the dimension should be 2 with some logarithmic corrections. Yeah.
Okay, thanks.
Okay. If you guys have no further questions, maybe we can wrap up at this point. So thank you very much again. And
Okay, thank you.
Paul.
So,
Hi, Nikos.
hi,
Thank you
hi,
for
Paul.
the talk.
Thank you for coming.